12 identical resistors, each with resistance R, forming the edges of a cube. What's the equivalent resistance between two opposite corners? It looks like an impossible tangle of parallel and series circuits. Take a guess before I show you. Let's label the corners A through H. Current enters at A, down here, and exits at G, the diagonally opposite corner. Now you could try tracing every path from A to G and combining them, but there are 16 distinct paths through this cube. There has to be a smarter way. The breakthrough comes when you stop thinking about paths and start thinking about symmetry. Look at corner A. 3 edges leave it, heading to B, D, and E, and by the cube's perfect symmetry, the current must split equally into all 3. Each edge carries exactly 1/3 of the total current, I over 3. This tells us something powerful. Group the 8 corners into layers by distance from A. Layer 0 is just A. Layer 1, B, D, E, the 3 neighbors. Layer 2, C, F, H, the 3 neighbors of G. Layer 3, G itself, by symmetry. All corners in the same layer are at the same voltage. Same voltage means we can merge them into one node. Watch the cube unfold. Between A and layer 1, 3 edges carry current. 3 resistors in parallel. Between layers 1 and 2, count the connections, B to C and F, D to C and H, E to F and H. That's 6 resistors in parallel. And from layer 2 to G, 3 more in parallel. A 3-dimensional nightmare just became 3 groups in series. Remember from physics class, N identical resistors in parallel give R over N. So the first group, 3 in parallel, gives R over 3. The middle group, 6 in parallel, gives R over 6. And the last group, 3 in parallel, gives R over 3 again. Now add them in series. R over 3 plus R over 6 plus R over 3. Common denominator is 6. That's 2R over 6 plus R over 6 plus 2R over 6, 5R over 6. Notice the middle layer contributes the least resistance, because 6 parallel paths give the current plenty of options. The equivalent resistance of a resistor cube is 5/6 R, less than a single resistor. And this makes sense. Even the shortest path from A to G crosses 3 edges, giving 3R. But all those parallel alternatives pull the total way down to just 5/6. So the key was symmetry. Equal distances from the source mean equal voltages, which collapses a 3D maze into a simple series circuit. Electrical engineers use this same symmetry trick when designing chip interconnects and power distribution networks. If you enjoyed this, like and subscribe for more.